All right. So we were doing acetal reactions before, is what we ended on. So real quick, let's look at some ketone and aldehyde reactions, just to remember what we had done. Okay. So what am I gonna get for the first thing? Yes, I'm gonna get an OH and a CN, so that's a cyanohydrin, right? So I'm gonna have an OH, a CN. I'm gonna add that CN to the carbonyl carbon, and there you go. What am I gonna get for the next one? What is two OHs called? It has a name. But you are right, it is going to be, I'm going to turn my carbonyl carbon into two OHs. It is a hydrate. Someone in the earlier class said it's a ho-ho. And I was like, no, that's a delicious chocolate treat. Calm down. All right, and then this last one, what am I going to make? I'm going to make an acetate. I'm going to remove the carbonyl, and I'm going to put two the oxygen in whatever's attached to them, whatever carbon's attached to them is going to end up on the carbonyl carbon. Right, so blue dot, blue dot, blue dot. All right, so we talked about acetals. We just briefly talked about how to make them at the end of last lecture. Right, generally you're going to have an alcohol. You're going to have a catalytic amount of acid. Our acids here are going to be PPTS or tosic acid, right? And that's going to make your acetal. The alcohol is always going to be in excess. Typically, it's going to be the solvent. Right? So you're just going to have a ton of this alcohol, right? There are two types of acetals, like broadly defined based on the structure of the acetal. There are acyclic acetals, right? Here, this is basically what we just drew up above. You have an alcohol, you have an acid, and the acetal that you make does not make a ring. Also, side note, like all of these are faces to me. Like all of these are just like, you know, a smiley face from being a dude or a dudette. Every single one of them. Now you can't unsee that. You're just gonna everything's gonna be like, oh, it's a lovely dude. All right. Or you have cyclic acetals. Here your acetal ends up being a ring. And you make these with diols. Sorry about the squiggle there. Here you have a 5-membered acetal, cyclic acetal. 1, 2, 3, 4, 5. Right? It's a 5-membered ring. And these two carbons here are the carbons here and here. Right? So you have 2 carbons between your alcohols and your diol. You have 2 carbons between your oxygens and your acetal. Right? Or you can do a slightly bigger ring. You can do a 6-membered ring. here you have 3 carbons between your oxygens. So you've got a 6-membered ring, 2, 3, 4, 5, 6. And these 3 carbons, 1, 2, 3, are the 3 carbons between your oxygens. And we're pretty much stuck at making 5 and 6-membered rings. They're the easiest ones to make. Smaller, they're too hard to form because they're too small of a ring. Bigger, they're harder to form because it's hard to get to make the ring because they're just too big. They flop around too much and the 2 ends of the molecule don't get close together. So pretty much it doesn't matter carbonyl and alcohol, right? As long as you have them and you have your acid, you're going to make an acetal. Right, so you just have to find your carbonyl carbon and then realize that whatever's attached to your alcohol oxygen is going to stay on that oxygen and you're going to get your product. You're going to get here isopropyl on both. Right, so this carbon is your carbonyl carbon. And then everything attached to the oxygen except for the hydrogen ends up being in the product. Right, then you have here, I've got 1, 2 carbons between my oxygens. So when I make my cyclic acetal, might have actually had an acid here. So when I make my cyclic acetal, I need to have 1, 2 carbons between my oxygens. Same thing here. This carbon here. Right, so you should be able to just look at something and go, okay, I have a carbonyl, I have an alcohol, I have an acid, I'm going to make an acetal. What kind of acetal am I going to make? Is it going to be cyclic or acyclic? Right? You know the difference because if you have a diol, it's cyclic. If you have just an alcohol, it's going to be acyclic. Fair? So mechanistically, how does this work? How do we make these? What is the mechanism? Right, so we're going to use kind of our simplest possible example here. So just like when we did the hydrates under acidic conditions, you have an alcohol plus you have an acid, right? The alcohol is going to react with the acid before anything else happens. I'm not going to make you learn the structure of toxic acid or PPTS. So you can just say that that is just going to be an H plus. You don't need the actual structure. So we're going to protonate our oxygen of our alcohol. Right, and this is what's actually going to react with our carbonyl oxygen. Right? So the protonated alcohol is what actually gives the proton to our carbonyl oxygen. So we have our alcohol. We're going to protonate our oxygen and regenerate our alcohol. So now we have made the carbonyl carbon easier to add to, right? It's a better electrophile now. So now our alcohol is able to add to the carbonyl carbon, pushes electrons up onto the oxygen. And we get here. Now, we need to get rid of our OH, right? And the way we do that is we need to turn our OH into a good leaving group. So we need to turn it into water. So what we can do is just have our oxygen grab a hydrogen off of our off of the kind of ether oxygen that we just added, and that's going to turn this OH now into water. Now I've got this good leaving group on my molecule, right? So now I can use the lone pair on my oxygen to push that water molecule off my molecule. Right, so this can come down and push my water off. Now I basically have an analogous structure to this right above it, right? I've replaced the hydrogen on my oxygen with now a carbon, right? But I still have a positively charged oxygen. That's going to make my carbonyl carbon easy to add to again. And I've got this excess of alcohol floating around. So once I get here, I'm going to push electrons up onto my oxygen. And now I am one proton away from having my acetal product. So then another alcohol will come by, grab that proton, push the electrons back onto the oxygen, and that's going to give us our acetal plus regenerate the protonated alcohol that I need to react with the next carbonyl carbon for carbonyl compound. So this kind of looks like a lot, but if you think about the hydrate mechanism, basically these steps, like to this structure, is basically just the hydrate mechanism again. The difference is in the hydrate mechanism, we pull this proton off with water and we're done, right? We have our hydrate, right? And then the second step is kind of just, for these steps here, are kind of just the hydrate mechanism again, right? So other than like this structure right here, which is kind of new, right? I go hydrate mechanism, change one little set of arrows, new structure, hydrate mechanism again, right? So I'm just repeating those same steps over and over. So it looks long, but it's two shorter mechanisms just kind of stapled together with a new step. So don't like let it intimidate you that like, oh, this was a lot of steps or a lot of arrows. It's just something that's simple that's stuck together twice to make it look bigger and scarier. Reasonable? So there's one really kind of important use for acetals that we're going to really focus on later on, but that is that acetals, well, let's say that aldehydes react faster than ketones uh, when we form acetals, and then that lets us use acetals as protecting groups. So I think protecting groups is a term that we haven't used before, so I'm going to define it real quick. So protecting groups hide a functional group so it doesn't react. So we turn one functional group into something else to protect it from whatever our next reaction is. So we hide it from the next reaction. And then to be a good protecting group, you have to be able to then easily remove the protecting group to get that functional group that you hid back, right? It would be like hide and seek, where it like hides and it easily comes out later on. You want it to be like a kidnapping where you gotta like beg your molecule and like, throw money at the molecule. Please give me back my functional group, right? That's a kidnapping. Protecting groups, they just hide, and then the functional group comes back and like, hey, what's up, right? So for acetals, like kind of our simple example of this is, let's say we have a molecule that has a ketone and an aldehyde. And we want to turn that ketone into an alcohol, but leave the aldehyde, right? Let's just ignore the aldehyde for a second. How do you turn a ketone into an alcohol? We went over it in the alcohol section. We went over it again at the beginning of this set of slides. Deep down, you know this. You're just being quiet to hurt me, and I understand. I understand. You don't like me. It's fine. It's fine, man. Right? So you can use like sodium borohydride, right? That turns a ketone into an aldehyde. No, try again. Use sodium borohydride. That turns a ketone into an alcohol, right? The problem is aldehydes always react faster than ketones. So if I try to treat this molecule with sodium borohydride, I'm not going to make this product, right? Instead, I'm going to react with the aldehyde first, and I'm going to make the alcohol, and the ketone's not going to react, right? So that's no good. That's not what I want. So what you have to do is you have to hide the aldehyde so it can't react. So because aldehydes react faster than ketones, I can turn it into an acetal. Right? Acetals don't react with sodium borohydride. So now I can add sodium borohydride. It's going to make my alcohol and leave my acetal. Now, the trick here is that acetals are in equal, like you can go from the acetal back to the carbonyl compound, right? So all the steps in the mechanism were in equilibrium because you could go forward and backward in each step. So here I can just add water and acid. The acid here can be something like PPTS, tosic acid, sulfuric acid, and this will then take your reaction or your molecule back to the carbonyl compound. So now I'm going to have my alcohol that I wanted, and I'm going to have my aldehyde. All right. So acetals are good at this because they're easy to put on, which is something you want in a protecting group. If you have to do if your protecting group's hard to get on, you're not going to want to use it. And then at the end, it's easy to get it off, right? So you don't have to like, you're not going to have to fight with the molecule or worry about like using harsh conditions. They're usually pretty easy to take back off. So it lets you hide the aldehyde, do reaction somewhere else in your molecule, and then get the aldehyde back later on when you need it. So this is one example. We've got a whole bunch of like examples coming up here in the future on protecting group synthesis, but this is kind of our first one. Reasonable? Seem good? All right. So We got acetals. Next thing on the hit list here is imine and enamine synthesis. So imines are the nitrogen analog of ketones and aldehydes. So this is a carbon that is double bonded to a nitrogen, and then the nitrogen is going to have some group coming off of it. Usually that group is a carbon chain of some sort, but this is an imine, right? So you've basically taken the oxygen from a ketone or aldehyde and replaced it with nitrogen bonded to something. And then we have enamines, which like deep down you knew what this was because you know what an enol was, right? So this is an enamine. We really went on a limb for this one. A double bond, it's an ene. On that double bond, you have an amine. We were like, enamine, name, done. Thank you for playing. Super easy, right? So while these two groups are related, how you get them is slightly different. So we're going to go through the imine stuff, and then we're going to go through some enamine stuff, right? So let's look at our imine. So in the simplest sense, right, you are basically taking the oxygen from your carbonyl and the two hydrogens from your amine and using them to make water, right? So you take the oxygen off your carbonyl, you take the two hydrogens off your amine, you make water, and in that process, you make your imine. Mechanistically, it doesn't work quite like that, but it's pretty close, right? The big thing here is your amine primary amines make imines. So if you're using a primary amine, you make an imine. Our acids here, PBTS and tosic acid are our acids again. So the same acids we use to make acetals, we use to make imines. So pretty much any primary amine is going to become, and a carbonyl is going to make an imine. So when your ketone is symmetrical, super easy, right? Doesn't matter how you orient the carbon group on the nitrogen. Doesn't matter what the carbon group is on the nitrogen. You're going to make one product. It gets a little trickier when your ketones are not symmetrical, right? So let's say we had, this is our ketone. There are two possible products you can make. You can make one where the two isopropyl groups are trans from each other, or you can make one where the two isopropyl groups are cis to each other. Right? I'm using the same terminology, cis and trans, that we use for double bonds because it is just a carbon-nitrogen double bond. That bond is not able to rotate. Right? This is more than likely going to be your major product, but it's kind of like a step too far to have you guys also predict if you're going to make the cis or the trans, because sometimes it is hard to tell. So for you, if I give you a ketone that's not symmetrical, just give me an imine, right? I don't care which isomer you give me, just give me an imine. Again, we're like in multiple choice land for a lot of our exams. So whichever imine is the imine that you would make, don't worry about if I give you the cis one or the trans one, just pick one, right? Because it can be hard to predict. Right, this one's relatively easy, but if the two groups on either side of the ketone are close in size, it's hard to determine, like, is it going to be 1-to-1? Is it going to be 60-40? Like, that's just too much thinking, right? Now, aldehydes, on the other hand, aldehydes are really easy, right? Aldehydes are always going to give you the trans product. So if you have an aldehyde and you have an amine and you're making an amine, you always make the trans product. Right. And that's because you're putting the two largest groups as far apart from each other as humanly possible. Right. So with the aldehydes, you always know that the carbon group on the nitrogen is going to want to be on the same side as the hydrogen. So if you have an aldehyde, I get to be picky and I get to say, always make the trans one. Right. I'll write it again so you can't forget. Right. Always make the trans product. So ketones, give me an imine. Aldehydes, give me the trans imine. So how does this work? What is our mechanism? How is this going to happen? Right. So again, we're going to go simple. Makes my life easier, your life easier. It doesn't matter which acid I use. So PPTS and tosic acid, effectively interchangeable for our purposes. So you can use one or the other. So exact same thing as we did for the acetal. The amine is going to be protonated by the acid that we add. Right? And again, we don't care about the structure of the acid. We just care about the fact that it gives us a proton. Right? And same deal as we did with the acetal formation. We're going to protonate our carbonyl oxygen with our protonated amine. So we've got our protonated oxygen. We've made our carbonyl carbon now. Easier to add to, it's a better electrophile. So now we're able to add our amine to that carbon. We'll push electrons up. We're in the same situation, right? I've got to get rid of my OH. So I'm going to just have my OH grab a hydrogen, off my nitrogen. Now I've got my good leaving group, my water, stuck on there. I need to push it off the molecule so I can use my lone pair on my nitrogen to push this off. So now I've got my imine, but I have one extra proton, so the nitrogen has a positive charge. An imine that has a positive charge on the nitrogen is called an iminium ion. So I've got to turn my iminium ion into an imine. So all I have to do now is take my imine that I have it grab this extra proton, push electrons onto the nitrogen. That's going to give me my imine plus regenerate my protonated amine that I need to react with the next carbonyl compound. So you should be thinking, he just wasted my time. He didn't teach me anything, right? Because this is basically the acetal mechanism. If you just erase the OH and put an NH2 in its place, right? They are the exact same steps. You're doing the exact same thing till you get to this last step with the iminium ion. And instead of adding to the carbonyl carbon, you're just like, I'll pull off that proton, it'll be done. Right? But it's the exact same mechanism. So you're doing the same thing. The only thing you're doing is you're doing it with nitrogen as opposed to oxygen. So I don't know. I haven't taught you 2 long mechanisms. I taught you like 1 1/4 long mechanisms because I'm just recycling all of my steps. Right. So that's how we get imines. So where do enamines come from? So the big difference between how you make an imine and how you make an enamine is what kind of amine you start with. If you're starting with a primary amine, you make imines. If you're starting with a secondary amine, you make an enamine. Again, our acids are exactly the same. So the only thing that changes is what amine you're starting with. That's how you get different products. So what the R groups on the amine are don't really matter, right? So, simple case, we can have 2 ethyl groups. Get an enamine. You could have a ring, let's say. We could have 2 rings. We could have a ring for our ketone. We could have a ring for our amine. Make an enamine. When you have symmetrical ketones, again, life is easy, right? Because there's only one way you can make your enamine. If your ketone's not symmetrical, right? You're going to want to make the most substituted double bond that you can. Remember, all the way back in organic 1, we said that tetra-substituted double bonds are more stable than tri-substituted double bonds, and tri-substituted double bonds are more substituted than more stable than di-substituted double bonds. So here, you're trying to make the most stable double bond that you can when you're making your enamine. And so that's going to be the one that is most substituted. So if you have the choice of this versus this is the one you want to make. You always want to make the most substituted double bond that you can. Now keep in mind, right, we still kind of have our base rules of, right, there has to be room for the double bond. Right, so this carbon already has 4 bonds, so I can't put my double bond there. So I only have one possible option for making my enamine. And that is to make it that way. Right? Don't go putting 5 bonds on carbon. That hurts me. Aldehydes are similar, right? If you're going to make an enamine with an aldehyde, there's only one possible way you can make that enamine, right? So my go-to aldehyde here. Right? There's only one way I can put that double bond because there's only one place you can put it. And I'll let this slide. If you give me cis or trans, whatever. It should probably be trans, but I'll let it slide. Just give me an enamine. So how do we get, what is the mechanism that gets us enamines? Again, I'm not going to teach you anything new, but I'm going to make you write it because it's going to go into your brain. It's going to be great. Right? So we've got this, we've got our secondary amine, got our acid, we have our enamine. So the mechanism is exactly the same as making an imine until the very last step. So everything else that we're doing is exactly the same as what we've done before. Right? We're going to protonate our amine with our acid. It's going to give a proton to our carbonyl. That's going to make it so our carbonyl carbon is easier to add to, so our nitrogen can add. Can't have 5 bonds to carbon, so you got to push electrons up onto the oxygen. We have a protonated nitrogen. We got to turn our OH into a good leaving group. Grab that proton. Now we just got water hanging off our molecule. These are nitrogen lone pairs to push that water molecule off. And we get back to our aluminium ion. Plus we have water. Now, what's different about this aluminium ion than the iminium ion when we made an imine is that there's no hydrogen on the nitrogen, right? So I can't just have my amine come, pull off the extra hydrogen off the nitrogen, and be done. But I can't just have an iminium ion, right? I can't isolate that. That's going to be a pain. It's going to be reactive, right? So what's going to end up happening is my amine is going to come in and do a reaction. It is going to remove a proton, but it's going to remove the alpha proton. It's going to remove the proton from the alpha carbon, right? So it's going to grab this proton because we just have to lose a proton. We have to lose this positive charge. So it pulls that proton off. These electrons will fall down here and then push the electrons up onto the nitrogen. So in the end, the nitrogen is still losing its positive charge because it's getting electrons, but it's getting electrons from the carbon-nitrogen double bond. So then this is going to give us our double bond and then make our nitrogen neutral and then regenerate our protonated amine for reacting with the next carbonyl compound. So mechanism is 100% the same until the very last step. Right? So they're the exact same thing until you get to the end. Fair?
We're exploring the concept of a dream within a dream.
So you might be thinking, we did primary means, we did secondary means. What if you did tertiary means? Tertiary means don't do this type of chemistry, right? Kind of the giveaway is they don't have a hydrogen to lose. They've already made 3 carbon bonds. They have no room to make any more carbon bonds. And you're not going to break a carbon-nitrogen single bond. So if you have a tertiary amine, you're donezo. It doesn't do anything. So all of our steps and all the mechanisms we've done for imines and enamines, they're in equilibrium. So that means if I have an imine and I add water and acid, I can have this come apart and go back to being the amine and the carbonyl compound I started with, right? My acids here, similar ones that we've used before, PBTS, tosic acid, or sulfuric acid. So just like we can take an acetal and turn it back into the alcohol and the carbonyl, we can take an imine and do the same thing, right? We add a whole bunch of water and acid, and it'll go all the way back to the amine and the carbonyl. Enamines, same deal. They will unzip themselves and go all the way back to carbonyl compound and amine. So what kind of product are we going to make for the first one? So I have a secondary amine and a carbonyl. So secondary amine means enamine. So I'm going to make an enamine. Is my double bond going to go to carbon A or carbon B? B. Now for the second one, what am I going to make? Acetal, a cyclic acetal, yep. And again, here's my carbonyl carbon. Here it is here. Here are my two carbons, 1, 2, 1, 2. And then for the last one, what am I going to get? I'm going to get an imine. And because it's on an aldehyde, I'm going to get the transimine. So there you go. We'll pick up what happens when you change the nitrogen nucleophile, what functional groups you get. With that, I will see you here in a little bit. Take it easy.